Good afternoon, everyone. Firstly, we would like to thank the organizing committee of Line 19 for the opportunity to present our work, an autoregressive reinforcement learning approach for mixed integer linear programs. To guide you through our presentation, we'll first discuss some preliminaries and previous work, the motivation for our method, our proposed methodology, experimental results, and finally, some future work we are implementing and considering. Without further ado, let's dive into previous work. For non-autoregressive approaches, neurodiving and predict and search are some of the more prominent literature in the field. Neurodiving uses a bipartite graph convolutional network to predict marginal probabilities, which then employs a selective net trained via supervised learning to sample k partial solutions. Specifically, a partial solution refers to the assignment of a subset of decision variables. After sampling k partial solutions, it then solves each sub-MILP by fixing variables according to those predicted assignments. Predict and search also uses a bipartite graph convolutional network for predicting marginal probabilities, but selects the top K1 and K0 assignments based on confidence. And instead of fully fixing the variable assignments, they apply a trust region method, which allows for limited Hamming distance changes to the variable assignments, reducing the likelihood of an infeasible solution. For autoregressive approaches, we have RL-MILP and RL for branch and bound. RL-MILP is an iterative local search method which begins with an initial solution and repeatedly invokes a graph neural network to propose variable increments or decrements to improve the current variable assignments. RL for branch and bound is an approach to learn a branch and bound heuristic. Their approach employs certain techniques to allow for the use of the RL framework for model training. This is orthogonal to our work as it applies to the downstream solver. Our work focuses on the upstream partial solution generation. A key takeaway from approaches like RL for branch and bound is the merit of using imitation learning, which may be a viable technique that could be used to improve the performance of the reinforcement learning policy. Our motivations stem from existing limitations of previous work. For non-autoregressive approaches like neurodiving and predict and search, all variable assignments are predicted at once in a non-autoregressive manner. A major limitation of this is the assumption that variables are conditionally independent, which is usually not the case. Secondly, by predicting all variables at once, it increases the likelihood of producing infeasible variable assignments. Lastly, these approaches learn to model the probability distribution of the variable assignments and do not directly optimize for objective values and solver runtimes, which are important metrics in the real-world context. For autoregressive approaches, existing literature mainly revolve around applications in branch and bound heuristics and local search, but few approaches generate partial solutions directly in a sequential constructive manner that our approach proposes. Other papers like RL for CO aim at reducing the complexity of applying the RL framework to solve combinatorial optimization problems. However, the implementations generally require problem-specific graph structures and problem-specific decoding schemes. Our approach is designed to work across any MILP dataset. By constructing partial solutions sequentially, we overcome the conditional independence assumption, and through the embedding of our variable propagation algorithm within the RL framework, we are able to dramatically reduce the number of variables the learning model will have to predict. Our reward function is also crafted to balance two objectives, minimizing the solution's objective value and reducing the overall solver runtime. For our proposed methodology, we begin by representing the MILP as a bipartite graph of variable and constraint nodes, extending on prior work. The bipartite graph is being used as the state observation for our RL environment. At each step, we perform three stages. The first stage is state augmentation. This is done by incorporating the current partial solution as a variable feature and computing a tightness metric for each constraint based on those partial assignments. This will be elaborated later on. Secondly, we select a set of variable assignments. We pass the augmented features to an actor network, and the network predicts an assignment for each variable, a 0, a 1, or a 2, which indicates no assignments. We then mask these predictions against the existing partial solution so that no previous assignments are overwritten, yielding the updated partial solution. Finally, we pass this partial solution through our variable propagation algorithm. By embedding the variable propagation algorithm within the RL framework, we're able to yield a much larger set of variable assignments from a small number of predictions from the actor net, due to the inferred assignments we can set from detecting if constraints are too tight or relaxed. These three stages are repeated until a termination criteria is met. The partial solutions are then fixed with a specific decoding method to create a sub-MIP problem that we then solve to obtain the final variable assignments. In our paper, we extended from the neurodiving and predict and search paper by implementing the decoding methods they had used.
Now I'll be explaining our tightness metric. We first define the following terms with respect to a constraint. Left-hand side of the equation in red being a weighted linear sum of decision variables x, the right-hand side of the equation in blue being the constant term on the right, in the sense of the comparator, which is defined as less than or equals, more than equals, or equals. Next, we define the lower bound of the constraint, or more precisely, the lower bound of the left-hand side expression, given some partial solution y, which fixes the assignment of a subset of variables in x. A similar definition is applied for the upper bound of the constraint. We can then define alpha and the tightness T as below. This metric has the following properties. When tightness equals to 1, it means that the remaining unfixed variables in the constraint have a single combination of assignments which are feasible. Hence, the assignments of these variables can be inferred and propagated. When tightness is less than or equals to 0, it means the constraint can be relaxed. The degree of the variable nodes in the graph for each of the variables in the constraint can be decremented, and if the degree reaches 0, we can trivially infer the assignment of this variable by selecting the value which optimizes the objective. Lastly, when tightness is more than 1, it implies that there is no feasible assignment of the remaining unfixed variables in the left-hand side. Without running a solve, we are able to determine that the partial solution is infeasible, and we terminate the trajectory. Now we can use this tightness to determine when to propagate, and in the next few slides, we will cover the two cases, tight constraints and relaxed constraints, given a partial solution. For tight constraints, consider the following example. We have a problem with the constraint x1 plus x2 plus x3 is less than or equals to 1, given the partial assignment x3 equals to 1. We can then compute the tightness T accordingly, which equals to 1. From here, we can infer the remaining unfixed variable assignments x1 equals to 0 and x2 equals to 0. Now let's look at a different example to show the effects of relaxing constraints. Consider a problem with the following constraints as shown here. Given a partial solution x3 equals to 1, we can relax constraint 1, C1, which decrements the degree of the variable nodes x1 and x2. This means we decrease the number of constraints for variable x1 from 2 to 1, and the same can be applied for x2. This, however, does not allow us to immediately infer any assignments yet. Now consider when we add to the partial solution x4 equals to 1. We can now relax additional constraints C2 and C5. If we follow the same procedure as before, we notice that the degree for x1 is now 0, as it has no remaining constraints tied to it. Therefore, we can infer the assignment of x1. If the objective coefficient a1 of variable x1 is positive, then we assign x1 to its lower bound value 0. Otherwise, if the coefficient is negative, we assign x1 to its upper bound value 1, which would ultimately minimize the objective. For the following sections, I'll be covering our model implementation and details into our reinforcement learning framework. We opted to use proximal policy optimization to train our actor network, which also requires a critic network. Both of these modules share an observer graph neural network, which extracts node level and graph level features from the input graph states. The observer GNN is pre-trained through supervised learning via a one-step variable prediction task. Similarly, the actor network weights are warm sorted through behavior cloning, following a heuristic policy. This heuristic policy generates trajectories through the assignments of a subset of zeros and ones, which are sampled from a reference solution obtained by a base solve. This is required because the action space is combinatorially large, and the initial distribution of selecting zeros and ones is far from the target distribution of a good policy, which makes it difficult for the model to learn quickly. Next, I'll be covering the reward function used. The reward design is as follows. We break down the reward into several stages. If the termination condition is not met, then we only return an exploratory reward, which contains an action reward, RA, and a step penalty, RS. Otherwise, the termination condition is met and the current partial solution is final. We can now solve the SEP MIP given this partial solution to obtain its feasibility and performance, meaning the optimality gap and the solver runtime. If the solution is infeasible, we add a feasibility penalty RF as shown, which reduces the reward according to the percentage of violated constraints. Otherwise, we add an optimality reward RO, which minimizes the optimality gap. And lastly, if the optimality gap is near optimal, meaning it is within a set threshold by the user, we add an additional time reward RT, which increases proportional to the percentage speedup. In the equation, BST and CST refers to the base reference solve time and the current solve time, respectively. Now let's look at the action reward, RA, which functions as an exploratory reward signal and avoids a sparse reward landscape. This is designed as a heuristic to guide the policy with two things in mind. First, the number of ones assigned should be non-zero. Since the solutions for these problems expect a large number of zeros and few ones, predicting on zeros is not informative. Secondly, the number of twos assigned should be a large percentage of the action. This is because large assignments of ones and zeros are more likely to reach infeasibility. Now I'll be covering our experimental results. We performed our experiments on the following datasets: the set covering problem, the combinatorial auction problem, and the generalized independent set problem. The formal problem formulation is as shown on the right for each of these problems. We use Groby as our baseline optimizer, running each instance with a hard time limit of 300 seconds. By capping the solve time, we emulate a real-world time crunch, so many instances are not solved to optimality within this time window. In other words, the best objective returned by Groby may not be the true global optimum on every test case. In particular, for slightly harder problems like the CA and GISP instances. This gives room for RL-driven approach to discover better solutions within the same time budget. Now I'll cover some results regarding the propagation introduced by our method. Our framework learns both which variables to assign and how many, whereas predict and search, or PNS, requires manually specifying K0 and K1, which are the top K marginal probabilities closest to 0 and 1 respectively. The right-hand side of the table shows, for each dataset, the average number of predicted assignments alongside the number of propagated zeros and ones. Compared with PNS, the numbers show how our method minimizes the number of predicted variables required to obtain a high-quality partial solution that directly optimizes for solver speedup. We note that for SC, the partial solution generated for our method on average consists of few zeros and ones, while PNS predicts 500 zeros and 0 ones. This discrepancy is due to the nature of assigning ones for the SC instances, where the number of ones assigned to the solution is very small. More interestingly, for CA and GISP, we see the effectiveness of the variable propagation. With a much smaller prediction of zeros and ones, the propagated size of the final partial solution is comparable to the PNS method. Finally, these are the results of the average primal gap plotted against calibrated time for the three datasets. Calibrated time, following the neural diving paper, is the wall clock time scaled by the time taken to solve a small reference instance. and this helps to reduce the variance of the results. Now do note that the best objective value in this case refers to the best known objective obtained by the base reference solve, which is within a limited time. Hence, the primal gap plot can go below zero, which implies our method's ability to find a better solution within the time limit. For SC, our method obtains a 75% speedup compared to the base solve. And for CA and GISP, our method finds a better For GISP, our method is both faster and finds a better solution than the base solve. For future work, we are looking into the following directions. We would like to better handle infeasible trajectories rather than just terminating. This can be handled by using some repair mechanism, such as having a separate train destroy policy. Another direction to explore is other GNN architectures, particularly graph transformers and their use of attention mechanisms. Thank you for listening and feel free to send any questions regarding our work.